This project has been funded with support from the European Commission. This publication reflects the views only of the author, and the Commission cannot be held responsible for any use which may be made out of the information contained therein. We'd like to welcome you to our a little bit longer than little digital presentation about the electromagnetic spectrum of electromagnetic waves. We especially like to welcome all the students coming from the schools participating in the Erasmus Plus project. By the way, you can also enable the subtitles for this video on YouTube. They are working fine. At first, we want to explain what electromagnetic radiation really is. If you already know this, you can of course just skip right ahead to the spectrum. Actually, electromagnetic radiation consists of electromagnetic waves, which are propagating through space. Like mechanical waves, electromagnetic waves have a wavelength, which is the distance between two crests or two thugs, or simply the distance the wave covers in one oscillation or in one period. Also, they have an amplitude and a frequency, which is measured in hertz, so how many oscillations the wave does per second. The big difference to mechanical waves is that the electromagnetic waves travel with a constant velocity throughout vacuum. This means that electromagnetic waves do not need a medium to extend in. Classical mechanical waves cannot move without a medium. Shock waves, for example, need air and pressure, and water waves, of course, they need aqua. On the other hand, a constant velocity means that the wavelength and frequency of electromagnetic waves are dependent on each other. The real interesting point about the electromagnetic radiation comes up next. In reality, electromagnetic waves are synchronized oscillations of both electric and magnetic fields. So the wave generates both an electric field and a magnetic field. The two fields and the ability of the wave to travel in vacuum are caused by an elementary quantum physical concern, that the electromagnetic wave is actually driven by a particle, the so-called photon particle. The particle itself has a mass of zero, so it does not contradict with the requirement of the waves to only carry energy. Also, its spin is the reason for the sudden and chaotic movement. Photon particles are the quanta of all electromagnetic force, and a quantum is the minimum amount of a physical entity needed for a physical interaction, in this case electromagnetic interaction. The photon particle is the electromagnetic interaction particle. Without it, no electromagnetic effects would ever be possible. Electricity wouldn't be possible. This is super important. Also, the third Maxwell's equation proves that any magnetic phenomenon is directly connected to an electric phenomenon. This makes sense considering that electromagnetic waves are synchronized oscillations of electric and magnetic fields at the same time. Now we are going to investigate the electromagnetic spectrum, because what's special about the electromagnetic radiation is that different frequencies have different effects on matter, and because of this, electromagnetic waves get kind of characterized into specific radiations depending on their wavelength and frequency, source of emergence, their composition of energy, and benefits to our life. We will be going to explain all kinds of radiation, from radio waves to the cosmic waves and gamma rays. The first wave, with the lowest frequency and the highest wavelength, are the radio waves. They were discovered in 1887 by the German scientist Heinrich Hertz. They are mostly used for wireless transport of information. However, there are multiple utilizations: communication, remote control, and also target locating by devices like radar and sonar. The data transfer is working by very simple technology. The transmitter, or also called sender, transmits or sends information per antenna on a radio wave, which again gets received by an antenna of a receiver. So let's look at the simple transmission of a voice signal. In the microphone, first off, the sonic signal gets transformed to an electric signal. This signal has a problem. It is way too weak, so we reinforce it in an amplifier. The signal then gets modulated on a carrier wave and gets sent after passing by our output filter. Vice versa, the receiving works kind of the same. At first, we want to filter out all that noise and the unnecessary inputs, so we get our raw signal. That will be mixed and demodulated from the carrier wave. Afterwards it's again too weak, and we must amplify it again before we can blast it through our speaker. This was all therefore just the explanation of the function of a simple radio application. What we want to know now is how radio waves get emitted from our antenna exactly. For this we at first need a simple LC circuit, which consists of a capacitor with a specific capacitance and two capacitor plates, a circuit, and in this circuit integrated a coil with an inductance depending on the amount of convolutions the coil has. So what will happen if we put on a charge on the capacitor is that this charge wants to get over to the other capacitor plate. This results in a voltage, and this voltage now causes the charge to flow to the other side as a current. The important part now is that the coil generates a magnetic field when the current is entering it. This is explained by the Maxwell's equation, which asserts that whenever there is a current, there is also a magnetic field. Now the other plate of the capacitor is charged while the other one is discharged, leading again to a voltage. Now the current flows in the opposite direction, also creating a magnetic field, now in the opposite direction than before. The direction of E and B field are explained by the Lenz's law. If we examine this a little bit more accurate, the LC circuit is nothing more than an electromagnetic pendulum swinging from voltage to current and from electric to magnetic field, instead of from right to the left, and we can use this oscillation for the emission of radio wave. The problem is that the frequency, which is also calculated by this equation, is way too weak, so we need to amplify it somehow. At first we need to reduce the inductance, which we can do by reducing the numbers of convolutions. Then we also need to reduce the capacitance, which depends on the distance between the two capacitor plates, so we need to increase the distance. When we do that, the result looks like a line called the Hertz dipole, which is nothing more than our conventional radio antenna. As you can see here, the constant change of E and B field is now happening on our antenna. This leads to the emission of radio waves. Now we want to clarify the modulation of our information signal. As I said before, our information signal is way too weak in its frequency. So what we do is we modulate our low frequency information signal on a high frequency carrier wave. This can either be achieved by modulating the information as a change of the carrier wave's amplitude on the carrier wave, called the amplitude modulation, or by modulating it on the carrier wave as a change of its frequency. You may know these two concepts from the car radio eventually. The next utilization of high radio wave frequencies and also already weak microwave frequencies is the radar. The simple principle of the active radar or sonar explains that from the sender transmitted radar wave gets reflected from the target it hits, and the transmitter, which is also the receiver, can detect the reflected waves and though it calculates the position the target is in, so the degree, the distance and the height of the target to the transmitter. Now, many of you may know that there are also planes which are nearly completely invisible to the radar, such as this B-2 stealth bomber. On the left side you can see a conventional fighter, which is reflecting the incoming radar waves back to the sender. These waves mostly get reflected at the fighter's edges. However, at this F-117 this is not the case, because its cover consists of a keen amount of rectangles, and these rectangles are not reflecting the waves linear back to the sender. Instead, they reflect them in a different degree into the sky. And this leads to a significantly lower radar signature, which you can see here. A conventional non-stealth plane has a much bigger signature. The next type of waves are the microwaves, which again are used for target locating, but can also be used to heat up water molecules, like in this microwave oven. How is this now happening? At first, you may know that water molecules specifically are dipoles, so they have a plus pole on one side and a minus pole on the other side. We can use the electric field of our electromagnetic waves now to bring the molecules to bounce. This constant motion is nothing more than kinetic energy, which again gets converted to thermic energy, in other words, heat. This interaction is caused by the oscillation of the electric field, which reacts with both sides of the water's dipole and brings it to oscillate as well. But this is only working on a specific area of frequency. The frequency must be in range of the water molecule's resonance frequency, so we get a constant reinforcing effect on our water molecules. Other frequencies will just cause the molecule to bounce once and to return it to its motionless state afterwards. Ideally, this frequency is at around 2.5 GHz.
The next higher frequency belongs to the field of infrared radiation. As you can see on the pictures, infrared has various utilizations. For instance, infrared can be used as a heater. Here it is utilized to prepare a meal. Although infrared has pretty large wavelength, it still transmits a high proportion of thermic energy in comparison to other radiations. The highest temperature of about 690 degrees Celsius gets achieved at a medium infrared wavelength of 3 to 8 micrometers. Another usage of infrared is the thermography. It means to detect infrared radiation through an infrared spectroscope. The emitted intensity will be populated with pseudocolors to clarify in which areas the highest infrared emission occur and in which the lowest. This method is used to analyze heat seals and heat distributions. For example, the infrared image shows the heat sealing of a house. The darker the color, the less infrared is detected, and the better the sealing is. As you can see, the windows are quite heat permeable, while the roof is nearly completely sealed. In the medicine, thermography provides a safer alternative to mammography. For instance, breast cancer and inflammations can be diagnosed. On the left side of the slide, you can see an unhealthy, while on the right side a healthy breast. On this picture here, thermography shows the heat capacity of a polar bear. Although his fur is believed to be white, it is actually completely black, and therefore absorbing infrared radiation, which results in almost a complete heat sealing. This allows him to survive in harsh environment and provides a beautiful example of adaptability. The next higher frequency, exactly between infrared radiation and ultraviolet, is the visible light. It is the only radiation which our eyes can see, which is why it is called so. The visible light intends the area between 380 nanometers and 780 nanometers. The way how light is composed is beautifully shown through a glass prism. When a beam of pure white light hits our prism at a certain angle, it gets refracted into all of its components, so from red light to violet light. As you can see, all the colors we perceive are present at the same time in light. How we see it is just a matter of how light gets refracted. The phenomenon which describes this is called the dispersion. Scientifically expressed, phase velocity depends on its wave frequency. The result is a spatial separation which is happening when light passes through a medium with a different density. As you can see here, violet and blue light is refracted more easily than red or orange light. The diagram on the right side shows the refraction index for the case in which light is entering glass. Shorter wavelengths have a higher refraction number, which means they are stronger refracted than longer wavelengths, like infrared. Here you can see a lot of phenomena of dispersion: the glass prism, a rainbow, and sunset. At the sunset, the sun is perceived redder than at the rest of the day. This is because the actual position of the sun is beneath the horizon and all components except the red parts are refracted into a, from our position, not visible degree already. From what we know from the previous diagram, red light is not as easily refracted, so it still is seen significantly. and we assume a wrong position of the sun because of the refracted red light. The sun is still visible even though it has passed by our horizon. Another phenomenon of dispersion we all know is the rainbow. Here, the sunlight is refracted into its components by a water droplet. As we get further and further into higher frequencies of electromagnetic radiation, it is important to comment on the energy content and how it depends on the wave's properties. The German scientist Max Planck has discovered a way to calculate the amount of energy of a specific wave by multiplying its wave frequency with a constant value known as the Planck constant. Because of the frequency is dependent on the wave's length, we can also calculate it by using the velocity as well. The most important thing to notice is that the higher the frequency is, the higher the energy content of the wave gets, which is super important for our next slides. The next radiation type is the ultraviolet. Sunlight contributes about 10% of ultraviolet. Other sources that emit ultraviolet rays other than the sun may be mercury vapor lamps, black lights, and electric arcs. Ultraviolet light causes many substances to fluoresce, and as you know, ultraviolet radiation has both beneficial and harmful effects to life. There are three types of ultraviolet radiation that vary from harmless to being even deadly. Far ultraviolet or UVA radiation has the least amount of energy because of its high wavelength, thus being not very harmful to biological cells, while near ultraviolet or UVC can have a deadly impact on our life. Fortunately, it is completely absorbed by our ozone layer. Intermediate UVB, on the other hand, gets through the ozone layer and can cause major damage if it's not blocked, for instance, by clouds or by sunscreen. Another interesting side effect of ultraviolet light is the fluorescence. This phenomenon appears when a substance which has absorbed electromagnetic radiation is emitting a part of the radiation back as light on its own. The emitted light has a lower energy than the absorbed radiation in most cases. Usually, black light irradiation is the cause of fluorescence. X-rays were discovered in 1895 by the German scientist Röntgen, actually by mistake. He named the unknown ray, also known as a Röntgen radiation, X-radiation, because of the at first not clarified emergence. The X-ray is the first electromagnetic radiation containing enough energy to ionize atoms and to disrupt molecular bonds. Because of this, X-radiation is able to ignore somatic structure and is also blocked by harder materials like the bone, making it useful for different applications. Other usage may be medical CT and backscatter scanning, for instance for security checks. How does X-rays get emitted? Whenever a charged particle such as an electron of sufficient energy hits a material, X-rays are produced. In a simple X-ray application, electrons are first produced by a filament and then accelerated through an electric voltage between an anode and cathode. The then accelerated electrons hit the anode with a specific velocity strong enough to recoil an electron. The missing electron in one of the inner electron shells gets instantly replaced by an electron out of the outer shell, and so on electrons in the whole shell are moving to fill the gaps. Electrons on an outer shell carry more energy than the ones on the inner shells. This now missing energy gets emitted in form of electromagnetic radiation, called X-rays, and can be used for different applications. This form of emission is called the characteristic radiation. But also the radiation itself has an interesting impact on matter, which makes it so dangerous to our bodies. As you can see, X-ray radiation has sufficient energy to recoil electrons out of the outer electron shells. The photon kicks out the electron, which absorbs a part of the incident photon's energy as kinetic energy. The scattered photon is then lower in energy than the incident photon. This phenomenon is called the Compton scattering or simply Compton effect. The backscattering is used as a scanning tool, for example, at the airport security. The simple irradiation of a target allows the detection of the scattering, which again allows to calculate the size and the properties of the target. The object can be reconstructed taking the emissions into an account.
Now the next part we come to is super interesting. The so-called gamma ray, which differs from X-ray only through its emergence. The gamma radiation arises from the radioactive decay of nuclei. But there are also other sources, like the annihilation of electrons and positrons, and astronomical phenomena like the gamma ray or blazars and quasars. The ray itself is extremely dangerous to somatic structure and though needs to be contained, but is also used as a treatment for cancer. Some may know the gamma irradiation. For the sake of time, it is not possible to explain the radioactive decay, but it should anyways be already known, so we are going to explain the electron-positron annihilation instead. The positron is the antiparticle of the electron, having the opposite charge, and when a particle and its antiparticle collide, they annihilate each other. Gamma radiation then arises out of the annihilation, or in other words, energy. This is a beautiful example that we could use the annihilation of particles as a powerful energy drive, for instance in the astronautics. Another interesting phenomenon appearing in our universe as an example of extreme emission of gamma rays appears when a star dies and transforms into a black hole. To understand this so-called gamma ray burst, we have to put a look at how a star produces its energy, or simply said, how a star is lightening. Stars use nuclear fusion to produce an enormous amount of energy. Under extreme heat it is possible to fuse the two isotopes deuterium and tritium to helium. The mass of the one missing neutron can be calculated by Einstein's equation to the amount of energy we get from the process. So the star lives by fusing light elements to heavier elements. The problem is that at some point, or more precise, at the stage of iron, this process is not an exothermic reaction anymore, and the star needs to invest more energy to fuse the two elements together than it gets out of it. At this stage, the star burns most of its resources to achieve the nuclear fusion of this heavy element. As a result, the star gets bigger and bigger, trying desperately to maintain the fusion process. This happens always to the star at a certain time, but there are a lot of possibilities what exactly happens to the star. For example, a small star with a low density and a low mass like our Sun is most likely just imploding in a nova, to a planetary nebula, or to a white dwarf. But a large star with the multiple sun masses will at first evolve into a supergiant, surrounding its own planets and imploding as a supernova. At the climax of this supernova, the star again has a lot of possibilities. For example, it can transform into a super small neutron star with an extreme density, or it can form a black hole. And when a black hole is born, usually it emits a gamma ray burst for a very short time. This gamma ray burst has two jets, which are containing an extreme amount of gamma radiation or furthermore energy. A fun fact is that a gamma burst ricochet hit the Earth in the Ordovician period and caused a mass extinction. Two other phenomena with high emissions of gamma radiation are on the left side, blazars, and on the right side, quasars. Finally, we have the cosmic ray, which not only consists of electromagnetic radiation, but also of other particles. It is emitted from outside of the solar system, for example, from distant galaxies. Luckily, around 3/4 of the total radiation is soaked up by the heliosphere of our Sun. Upon the impact with the Earth's atmosphere, the rays can produce so-called air showers. These particle showers are divided into two types: the electromagnetic cascade caused by pair production and only being on an energetic level, and on the right side, the hadronic cascade, which is caused by the weak nuclear force creating a lot of different interactions, containing the production of, for instance, muons. So this is the end of our presentation now, and we'd like to thank everyone for listening, and if you have any questions, you can of course just leave a comment on the YouTube video.
Also, they have an amplitude and a frequency which is measured in Hz. So how many oscillations waves per second? The big difference to mechanical waves is that the EMW travel with a constant velocity throughout vacuum. This means that EM waves do not need a medium to extend in. Classical mechanical waves cannot move without a medium. The photon particle is the electromagnetic interaction particle. Without it, no electromagnetic effects would ever be route. Electricity would no be route. This is super important. Super important.